In this lesson, we're going to learn how to calculate the pH of a buffer solution. Remember, a buffer is a conjugate acid-base pair together in solution. And so there's one equation that I would like for you to use to calculate the concentration of hydrogen in a buffer. It's going to be Ka times a ratio of moles of weak acid, or in other words, HA, generic formula for weak acid, over the moles of its conjugate base. And so its conjugate base would be A minus. Remember, conjugate acid-base pair, they just differ by one H plus. So this is the one equation I would like for you to use. Just keep it simple, keep it very straightforward, because if you know this one equation, then you can use your pH equation, take the negative log of the molarity of H, and you'll have the pH of the buffer solution. So let's dive into an example here. We're going to take 1 mole of hydrocyanic acid and 4 moles of sodium cyanide. They're together in solution. They would like for us to calculate the pH of the solution. So first thing that I recognize here, I have a buffer. I have HCN, which is a weak acid, and I have sodium cyanide, and I know I can ignore the sodium ion because it's neutral and it's spectating, and I have Cn minus 1 ion. That's the conjugate base of hydrocyanic acid. So since I have both of these weak acid and its conjugate base together in solution, this is really a buffer solution. And sometimes this is the hardest part about a buffer problem, is recognizing that you have a buffer. So we're going to follow the formula above. The concentration of hydrogen is equal to Ka times the moles of your weak acid. And our weak acid here is HCN. Over the moles of its conjugate base, just knock off a hydrogen, and it's Cn minus. So we're going to plug and chug. H plus is equal to the Ka, 6.2 times 10 to the negative 10. Our moles of HCN, so 1 mole. And our moles of conjugate base, 4 moles, Cn minus. So the concentration of H plus is equal to 6.2 times 10 to the negative 10. The mole ratio here is 1/4, or 0.25. And I want you to pay close attention to this. I'm going to come back to that mole ratio in another problem. But our mole ratio is the most important thing here. But I'm going to go ahead and calculate the molarity of H plus. It's 1.55 times 10 to the negative 10 molar. So therefore our pH is going to be the negative log of 1.55 times 10 to the negative 10, and I get 9.81. Okay. Example number 2. We have 0.100 moles of hydrocyanic acid, that's our weak acid, and 0.400 moles of sodium cyanide. Again, ignore the sodium. We really have cyanide ion, which is the conjugate base of our weak acid. So again, we have a buffer solution. So H plus is equal to Ka, moles of the acid, HCN, over the moles of the conjugate base, Cn minus. Concentration of hydrogen, therefore, is equal to 6.2 times 10 to the negative 10. We have 0.100 moles of HCN over 0.400 moles of Cn minus. So that mole ratio of weak acid to conjugate base is again a quarter here, 1/4 as the first example. Okay, and we'll come back and talk about that just a little bit. Let's finish up the calculation. Okay, 1.55 times 10 to the negative 10 molar. It's our molarity of H plus. So pH is equal to the negative log of 1.55 times 10 to the negative 10, and you get 9.81 as your pH of this solution. So if I'm comparing example 1 and 2, I notice that I end with the same answer, 9.81. And the reason why we have the same answer, despite the fact that we have different quantities of the hydrocyanic acid and the conjugate base, is because first of all, we have the same conjugate acid-base pair in the buffer. And also, this mole ratio that I've highlighted, this 1/4 in both problems, okay, because the mole ratio is the same in both problems, the concentration of hydrogen is the same in both problems, so therefore your pH is the same in both problems. And this is really important to understand, that the pH of a buffer is determined by the Ka value and the mole ratio of weak acid to conjugate base. And if those two numbers are the same, those buffer solutions are going to have identical pH values. Let's try another example. Example number 3, we have 0.150 moles of ammonia and 0.500 moles of ammonium chloride together in solution, and they would like for us to calculate the pH. So I recognize NH3 ammonia as a weak base, okay, because of that nitrogen, that lone pair there is going to be really good at grabbing an H plus ion, act like a base. And you're putting it into a solution that contains a salt, ammonium chloride. Chloride, please ignore because he's neutral. I know that this is really ammonium plus 1, okay, the ammonium ion. That differs from our weak base by just 1 H plus. This is the conjugate acid of our weak base. And so again, we have a buffer solution. And the one formula I want you to follow for a buffer solution is H plus is equal to Ka of the moles of weak acid over the moles of the conjugate base. So our moles of acid, the acid in this buffer is NH4, and our base is NH3. Okay, so when you do this mole ratio part, it is always acid over base, and the acid is always the one with the extra hydrogen. So we're going to plug and chug here, but immediately I notice I have a problem. In my equation, I have to use a Ka value, but in the problem itself, it didn't give me Ka, it gave me Kb. So I first need to convert a Kb into a Ka value. So off here to the side, I know that Ka times Kb equals Kw. And Kw is a constant, 1 times 10 to the negative 14. So if I need to solve for the Ka would have to be Kw over Kb. And now I can plug in the Kw value, and that value is given to you on your equation sheet, 1 times 10 to the negative 14, divided by the given Kb value, 1.8 times 10 to the negative 5. So our Ka for this conjugate acid-base pair is 5.6 times 10 to the negative 10. So that's what I'm going to plug in into our buffer equation. So hydrogen ion is equal to 5.6 times 10 to the negative 10. Now for that mole ratio part, acid over base, 0.500 moles of NH4 over 0.150 moles of NH3. So you get 5.6 times 10 to the negative 10. That mole ratio is 3.333. Do not round. Keep the values in your calculator, please. So hydrogen is equal to a molarity of 1.867 times 10 to the negative 9 molar. So finish this up. pH will equal the negative log of 1.867 times 10 to the negative 9. And I get a pH of 8.73. Okay, so this one was done just like the other examples. The only difference here is that I had a Kb value of the weak base, and I had to convert it into a Ka before I could calculate the concentration of hydrogen. Example number 4. We have 10 milliliters of a 0.500 molar ammonia solution and 20 milliliters of a 0.0200 molar ammonium chloride solution. Again, same species, so I already know I have a weak base and its conjugate acid. Together in solution, we have another buffer. Okay, so we're going to follow the same format. The only difference here is that I wasn't given moles right away. They gave me volume, they gave me molarity, but I know that molarity is really moles over liters, and you really got to think about that. When you see that capital M, molar, it is really moles over liters. So anytime I have molarity, I can take molarity, whatever it is, times liters, and I always get moles. So I'm first going to calculate the moles of ammonia. So that's going to be 0.500 molar ammonia times its liters of 0.01 liters. And you're going to get 5 times 10 to the negative 3 moles of NH3. I'm going to repeat and calculate the moles of ammonium, NH4. And so we have 0.0200 molar NH4 plus times 0.020 liters. You get 4 times 10 to the negative 4 moles of ammonium. Okay, so now I have my moles of each component of my buffer. Now I'm going to use that one equation. H plus is equal to the Ka times moles of the acid, the one with the extra hydrogen, over the moles of the base. I already calculated the Ka in the previous example, so I'm just going to rewrite that here. 5.6 times 10 to the negative 10. And now it becomes plug and chug. 4 times 10 to the negative 4 moles of ammonium over 5 times 10 to the negative 3 moles of ammonia. 5.6 times 10 to the negative 10. And our mole ratio is now less than 1, 0.08. And finish up our calculation of H plus. 4.48 times 10 to the negative 11. So the pH is equal to the negative log of 4.48 times 10 to the negative 11. And I get 10.35 as your pH. Okay, so this is the same as example number 3. Just one more step at the beginning. You had to take your molarities and multiply by the liters to get the moles. Okay. I do want to give you a little strategy that might save you some headache with decimals, especially if this is multiple choice. I know that molarity times liters equals moles, but let's say you have a real difficult time converting your milliliters to liters here, and maybe you never move the decimal the right number of times, which is 3. If instead you took molarity times milliliters, you would end up getting something called millimoles. So I just wanted to show you an alternative way of calculating those moles for those of you who are interested. If I took molarity times milliliters, you're going to get millimoles, 1,000th of a mole. So in our problem, if I wanted to calculate the millimoles of ammonia, we would take the 0.500 molar NH3 times the milliliters of 10 milli, and we would get 5 millimoles of ammonia. Okay, notice how that math is so much easier. 0.5 times 10, just move the decimal point one time, boom, it's 5. Okay. I can repeat and do the same thing for ammonium. Its molarity is 0.02 molar times its volume in milliliters. Okay, and so I know 0.02 times 2 is 0.04. But I'm not multiplying by just 2, I'm multiplying by 20. So I'm going to take that and it becomes 0.4 millimoles of ammonium. A little bit easier on the math. And so when I calculate the hydrogen concentration, it's still going to be the Ka times that mole ratio, moles of acid over the moles of base. But this time I have used these millimoles, which I'm allowed to do because I simply care about that ratio. As long as you have the same unit in the numerator and the denominator for this ratio, it doesn't matter. And you'll notice here, if you finish up this calculation, that mole ratio is still 0.08 as we have shown above. That's the same number, 0.08 here and 0.08 there. So the reason why I'm showing you this is because I know sometimes we mess up on converting from liters to milliliters, and sometimes we don't have a calculator, and especially on that multiple choice, it's going to be a whole lot easier to work with millimoles rather than regular moles.